We're going to talk today about an overview of the electronics industry and assembly, as you saw in the handout. And in the abstract, you'll see some pictures and photographs and walk away with at least a familiarity how circuit boards are fabricated, assembled, and tested. So doing this as an overview up here. You know, years ago, when you look at automobiles, you could think about electronics and electrical. So if you would disable all the electronics in a car, the only thing you would notice doesn't work is the radio. Okay, everything electrical, as in spark plugs and all that, would continue to work, but there was very little electronics in automobiles. Today, I just listed some of the things that are on electronics in automobiles. It's a lot of primarily safety features, convenience features, navigation features. I'm sure you're very, very familiar with them, but the automobiles today are a lot different. And it's because of the electronics. A significant part of automobiles today is in electronics. So what I want to talk about today is PCBs, printed circuit boards, fabrication, a little bit on parts, a little bit on circuit board assembly, a little bit on testing, and if we have time, I'll touch base with something called box build. How many here are familiar with how multi-layer boards are fabricated already? Okay? Okay, you got some familiarity. Okay, very good. So the top surface that you see over here, you know, we've got the solder mask with solder pads, and then really circuit boards are really multiple layers of two-dimensional circuits. So if you look at this circuit here, this is actually about a 6-layer circuit board, so 6 semi-independent layers that are all connected with vias that go through the board. So the way electronics is done is you have individual layers as far as routing, and you connect one layer to another layer via these vias that go up and down, and then the circuits are connected on there. There's imaging going on, so it's a subtractive process. So you put materials on a circuit board and then you etch them off to leave a pattern. So you see about etch, and there's all kinds of photo masking, and then there's all kinds of routing that goes.
Copper-clad laminate. It's the main raw material in PCB manufacturing, and also one of the main factors for PCB quality. Material cutting. To cut the CCL into the designed manufacturing size. The radius for CCL corner is needed to avoid the scratch during production. Inner layer coating. To coat the photoreceptive wet film on the surface of the clean CCL. The requirement of clean room. 10K degree clean room. Automatic delivery machine. Automatic exposure machine. To transfer the pattern from the film onto the inner layer core material. Laser direct image system with high registration precision of 1.5 mil line width and without film. CCD, automatic exposure machine. Traditional exposure system with film and transfer the pattern from the film onto inner layer core material. DES, developing, etching, and stripping. To etch the unnecessary copper and leave the pattern in need. Inner layer AOI, automated optical inspection. Transfer the image to the machine with optical reflection. Inspect the open short issue by comparing with the original working Gerber. Cutting PP. Cut the pre-peg into the optimal panel size according to inner core material. Riveting. Rivet the inner core materials together with pre-pegs to avoid misregistration in the following production. Layup. Lay up the raw materials into multi-layer stacking. Pressing. Press the boards in high temperature and vacuum conditions. Press the layup boards to multi-layer PCB with heat pressing. Cutting edge. Cut the outlines of the pressed multi-layer boards. Mechanical drilling. Drill the PCB via holes by using mechanical drilling machine. Mitsubishi laser drilling machine. Min via hole 0.076 millimeters. PTH. Plate the copper in holes and to make sure the conducting. Panel plating. Thicken the whole copper and surface copper by plating. VCP. A machine with vertical copper plating system. A better copper plating performance could be achieved with the same manufacturing conditions of the same PCB part number. The workflow keeps almost the same between outer layer and inner layer pattern, while dry film and alkaline etching are used during outer layer pattern and with pattern plating process. Dry film laminating. Outer layer developing. Pattern plating. Outer layer etching. Solder mask. Coat all the circuits and coppers with solder mask ink and for the function of insulation. After the photopolymerization of developing, the solder mask ink remained and solidified. Silk screen. Print the legends on the PCB surface and for the use of identification in the following production. Immersion gold. To form a cladding material with high performance of inoxidizability and solderability. Routing. To route the customized PCB outline with CNC routing machine. E-testing. To inspect the open short issue for finished PCB. Flying probe tester. For the inspection of prototypes and small volume orders. FQC. Appearance inspection on PCB boards such as scratch, no solder mask ink, solder mask ink on pad, and so on. Automatic appearance inspection machine. The efficiency will be tripled comparing with human visual inspection.
Okay, I'm going to kind of move on from there. I want to give you at least a background on how boards are fabricated. PCBs are printed circuit boards. People call them PCBF for printed circuit board fabrication and PCBA for printed circuit board assembly. In the additive process, that basically is starting with nothing and building up the circuit board from the bottom up to the top. So you're printing out insulating material, conducting material, building it all up. And you can do that now with additive manufacturing or 3D printing machines. What I want to talk about now are components. So years ago, this was considered to be a pretty small component. You can see that in here. Some are much bigger than that. So I'm going to talk about components in this phase. But if you look over here, there's actually a component right here on this on the fingertip right here. So parts are certainly small. Okay, I put this on here to show three different things. Basically, in the 1960s, through-hole technology was in place, and if you look at upper left-hand corner in the 60s, these are all components that have leads that go through the board and are soldered from the backside. In the late 1970s, surface mount technology was created, and parts are soldered onto the top surface and onto the bottom surface of the board, so you got double-sided assemblies. And currently, you can tell a little bit by how much green you see. The green is a solder mask where there's no parts, but you can see all of the silver in here. That's actually solder. There's little tiny parts in here that you can't even see. So current technology is a mixture of through-hole and surface mount, advanced packaging, and sometimes direct chip attached. We take the semiconductor and directly attach it to the circuit board. thought it'd be good for you to have a feel for some of the components. So there's things called chip components, resistors, capacitors. It looks something like this. Plastic leaded chip carriers, PLCCs, quad flat packs. They're flat and they have parts on 4 sides. Small outline integrated circuits with the little leads here, J leads. Over on the right, I put these through-hole parts. These are called radials. You notice it just comes like straight out. Dual inline package is like an IC, which got little wings that come out that go through the boards. And then axial parts come out the sided parts, and they have to be bent in the manufacturing facility and then installed into the circuit board that way. A few other pictures, just throw out some acronyms. I'm not going to go through all of them, but every part's got a different acronym with it. And I'm just showing here a better picture of the dip and add axials, radials. These are some of the discrete components I've got shown up here. 0402s right on down. I don't know, this is a match head, so you know about the size of what a match head is. There's a little part right over here, 01005, so it's 10,000 by 5,000ths of an inch, things like that. Pretty darn small, so you can imagine trying to solder something like that onto a circuit board. So we have the technology to do that, and that is commonplace now. Very bottom terminated parts. How many? I know most of you are electricals. Are there any mechanicals in the room? Okay, so I'm a mechanical also, and so we need mechanicals in there to package things up. But from a structural point of view, this big pad on here is to take the heat from the component and bring it down into the circuit board. There's a number of different mechanisms by which you can do that. Now I'm going to talk a little bit about circuit board assemblies. So I've got some samples up here, and we've got some other information for you over here too about a meeting coming up and some other things about SMTA up here. But a lot of different kinds of circuit boards. There's RF circuit boards. There's like transformer kind of things. There's some heavy copper in here, a lot of current going through here. LEDs that you'll see in lighting, all kinds of different lighting. These are actually what they call rigid flex boards. It's rigid pieces of circuit board with some flex circuits between them, so that you can basically bend the circuit boards around different things. Small boards, back planes, power supplies, transformers, and big power supplies over here. So there's a lot of different kinds of circuit boards. So what I'm going to do right now is, how many people have been into a surface mount assembly facility before to see how components are placed on circuit boards? Okay, good. So this will be a new thing for you. Anyway, so I got a picture up over here about a typical high-end factory. It's not a clean room per se. Semiconductors are in a very clean room, normally like 10 parts per million. Typically these around here, you'll see the smocks, but the smocks aren't in there for cleanliness. The smocks are in there for ESD, electric static discharge. The components are very sensitive to static, and the floor is conductive, the smocks are partially conductive, and there's a mechanism by which you can drain all the static electricity that you create in walking across the floor so it doesn't get onto the parts. And what I'm going to show you here is some of the machines. Basically, you load up the circuit board on the left-hand side and you unload it on the right-hand side. And when you're in production, you don't have to touch the boards all the way through unless you've got a manual operation you want to insert into it. So we're going to talk about printing paste onto a circuit board, which is the solder paste. And then there's a solder paste inspection machine. We have to make sure we put it down, make sure we inspect it, we did it right. And then there's placement machines that automatically place components onto the circuit board. And then if there's a manual add station, that's what this is. And then there's a reflow station where we convert the paste into conductive solder. And then coming out of that, we then move into automated optical inspection. So we're moving away a lot from operators and inspectors 100% inspecting every board. Every board is 100% inspected by the machines, and then the operators make a call at the finds that the machines have. So I'm going to click on an illustration here, and you'll see what in this, you'll see the stencil, and you'll see the machine, and you'll see a bar And what it's going to do is take solder paste that feels like toothpaste. It's going to push it through holes in this stainless steel stencil. So there are laser cut holes in the stencil like this, and wherever there's a hole, it will deposit that solder paste inside the hole. And then when the stencil is pulled up, it leaves the solder on the circuit board over there where it's supposed to be. So I'll click on this here and see what that looks like here for you.
Solder paste not only performs the function of a physical interconnection material, but it is the structural support, thermal interface, and conductor. It is critical to the manufacturing process that the correct amount of solder is applied in exactly the right place. We can accommodate a wide range of print formats. A laser-guided printer uses a scanning camera to quickly locate the fiducials and align the tooling and the PCBs accurately, while the transport system processes the boards with a minimum of handling time, and the solder paste height detection system guarantees the correct height of the fillet. The easy-to-use touchscreen makes programming faster and more precise. The printer prints and inspects each pad and solder joint after the solder is applied, ensuring the accuracy and reliability of the printing.
Okay, so this is kind of an illustration too. So you've got the squeegee over here pushing the solder into it, and you see the solder paste over here. And I put this out here so you can see that it just puts solder just on the precise locations that the component is going to be mounted to. So the solder at this point is not reflowed. It's tiny spheres of solder that are held up in a flux. So it's literally a paste sort of thing. And then the parts are then placed in that paste, and the flux and the paste actually helps hold that component down. And then because this is an inline versus a batch, between every one of the machines there's a conveyor. The conveyors are adjustable, typically from 4 inches to like 18 inches wide. So you would set up a line, adjust all the conveyor rails to the proper heights, and all the circuit boards will move through the line. So obviously you want to make sure that you have something on the edge so components aren't going over the edge of the board. So there's a lot of things when you design circuit boards that you know how to design them so that they go into manufacturing. And whether you're a EE or an ME, you got to make sure the parts on the board are placed correctly. There's 2 different component placement machines, basically. One places the small parts very, very quickly. There's a lot of small parts on the board, and there's typically a few very large parts on the board, like your ICs and things like that. The ICs are much larger. They have to be placed a little bit differently with a lot of optical verifications as you go through. So I'll show you the chip placer, but the other one's basically the same, just as in a different scope. So we're a little bit limited on time, so I'm just going to show you this one here. But it'll start off at speed and slow down. So I slowed it down right here so you get a feel for what it's doing. It's picking up parts here with the 2 heads and looking at it and then placing it down on the circuit board. Okay, so you can add a little bit of a feel there. Now that's not really called a high-speed machine. It's fast, but there are machines that are much faster than that. That machine it's mostly a high-mix, low-volume machine. So it's set up to easily put the parts on there, download the programs, but there's some machines that are much faster than that. But that is still pretty fast if you look at placing parts on a circuit board. There may be 1,000 parts on a circuit board, so it may be on the machine for 30 seconds or 45 seconds on it. The parts in a high-speed machine are put on what's called tape and reel, or they can be put in matrix trays like you see over here with some of the larger ICs. But you might have anywhere from 1,000 to 5,000 parts on these reels, anywhere from a 4-inch reel to a 12-inch reel that you have all these parts. These reels are put onto feeders you look at this is a feeder. So the reels are put onto the feeders are put onto the machine, and while the machine is running on a different product, you can load up the feeders with your next job on here to kind of minimize the amount of time that it spends on that particular device. Years ago, there were machines that automatically put some of these through-hole devices on there. Nowadays, they don't have too many of the older machines to put the obsolete parts down, but there's still connectors, power devices that right now are hand installed because there's only a few of them on there. But I put this in here so you can get a feel of the mechanical part when the pins go through the holes and then the screws attach to it here. And then when you solder it, a wave comes on the bottom here and does a fillet on the top, and it wicks all the way through to the bottom, to the top to the bottom here. So that's how the interconnect electrically and mechanically is made. Moving after the placement of the parts onto the flux and the solder, it has to go through an oven, anywhere from a 7 to 10 to 12 zone ovens. There's a pattern that you can see in the lower left corner over here, which is the temperature that the flux and the rosin within the solder have to be run in order to get the proper wetting. So the boards are slowly heated up, and they run for, let's say, 30 seconds in the molten state, and then they're cooled down properly. That's to activate all the items in the flux, so you get a good solid connection in there. Over here on the right, I put a picture of a solder paste. You can see it. It's got a lot of little tiny solder balls in there, so this is like a before picture of a solder joint. And I'm going to show you something here from a mechanical perspective. It's called self-aligning. So if you see this is a paste here, and it's going through an oven right now. You'll see as this solder becomes molten, this chip device comes up, and it actually adjusts and aligns, self-alignment to both sides. So there's a surface tension here and a surface tension over here, and it balances the forces out to show you how a real-time view of what that soldering process looks like in here on that. And I'm not sure. A ball grid array is basically another type of device. It's got solder balls. This is the device, the package up on top. The bottom is the circuit board down here. Right in here, there's the pad that's got some solder paste on it. But on these, it's got a solder balls that are attached onto the bottom of the component. Then it moves into the reflow oven. As it reflows, all this stuff will turn molten and turn a little bit shiny. And then as it liquefies, this top part will fall down and the ball collapse. So you'll see it actually fall down and collapse. So you kind of see that here. You see the paste on the bottom, balls on the top. It's going liquidus right now, all melding between. And there's the ball collapse. And you see how nice and uniform that they are. There's no short between one ball and the other ball going through there. Anyway, that's a very interesting picture in what happens inside the oven. Okay, now years ago, operators had to just look at every single solder joint on a circuit board. Now we have AOI, which is an automated optical inspection machine, and it's basically an optical comparator. It looks down on the parts, it knows what parts are supposed to be there, what the orientation, the symbolization that are on there, and it'll look at, let's say, a dozen parts at one time very quickly. Look through the entire board. Anything that looks unusual or out of place, it will flag to the operator, and then the operator makes a call about whether it is a actual failed part or not. If it's failed, it goes into rework. If it's just a cosmetic thing, then the inspector can let it go through. So the inspector actually makes the call of defects versus good parts. see by that, it did like 3 screenshots per board. So it actually, in the time you saw it, inspected all, 12 of those boards, something like that. So you get a feel. And then you saw a red light come in at the end. That means there's a defect on the board. And then it would go to that location, and the operator would call about whether it is a true defect or not. So they'll have to look at maybe 1 or 2 questionable things on a whole circuit board rather than potentially looking at 1,000 sites on that board. So I talked about how you solder surface mount parts, and we'll talk about now how you solder through-hole parts. So years ago, there was another wave that was done. I'm not going to touch on that here today. So I'm going to touch on something here called selective solder. So if you look at the through-hole parts that I talked about, the pins go through the circuit board, they come out the bottom of the circuit board. You have to apply solder to the bottom of the circuit board. It has to wick up along those leads and come out the top. So what you're going to see in this video, this is a machine that does leaded solder. This is a machine that does lead-free solder. If you notice that the circuit board is mounted into the machine here, there's optical cameras that are up on top to help align the top to the bottom. There is a nozzle on the bottom of the machine, and this nozzle has liquid solder pot right below it, and it pumps the molten solder up through this nozzle and streaming it out of the top. And then it moves along on the bottom side of the board to solder all of the pins that are in the through-hole connectors. So I want to give you a feel for what it is description-wise so you know what you're looking at here. So this is actually looking at it from the bottom side of the circuit board. So you see the solder mask, the green stuff, helps isolate the solder so the pins don't short from one to the other. We don't want any exposed base metal, that's why I soldered that. And this is a 180 pin connector, and you can see as it moves through here, and the board is kept kind of warm, but what really does the soldering is this molten solder coming across, and it just moves in an XY location on the bottom side of the board to solder all those. You can see that this is a whole lot faster than trying to hand solder some things over here. So that would take somebody a long time to hand solder something like that, and this is actually much more accurate and much more uniform in doing that. I want to move on to test right now. I got 2 slides on test. There's a continuity test about are all the parts put on the board correctly, and then there's a functional test, which is on the next slide. So there's basically a fixtureless test, which is called a flying probe test. There's no hard fixturing in here. It's just these probes that are pre-programmed to move around the circuit board and make contact. So for the double E's that are over here, if you're looking at a circuit board and you take your meters or your scopes and you hit power and ground and signals and all that, looking at what the signal is. Well, this is doing the same thing, making sure there's no opens or no shorts on the circuit board. So it's doing power to grounds and all of the continuity, make sure you got some of the right values of resistors and capacitors on there. And that's what we see over here. And then this is a bed of nails tester, which basically may have 4,000 pins in here, and all 4,000 pins may hit the circuit board at one time. And then within the software, you do all your electrical testing. So I'm going to show you a flying probe test over here. So you at least get a feel for how this machine would act a little bit faster than a human that's using probes. So there might be 8 probes on the top of a machine like this, and 3 or 4 probes on the bottom side of the same circuit board running at the same time. I think you got a feel for what that's like. It kind of looks kind of bionic and kind of freaky jumping around on there. It's obviously a whole lot faster than an individual technician trying to do that. The bed of nails tester is not any moving parts, but I'm showing a fixture on the right-hand side. and it touches the pads. From a design perspective, EEs or MEs, you've got to have enough space on the circuit board and enough little pads over here. So I put this picture over here where you've got the component over here with the lead, and then the pad sticks out a little bit with the little test pad over here. So you have to identify what parts of the circuit you want to put test points on. And you have to have little hooks on some of the ends of it to make it accessible. And you can't put test points underneath the components and things like that. They got to be accessible. There's a certain amount of angle that you need to be able to address every one of those here. So I'm going to let this run a little bit. This is something called boundary scan or functional test. So functional testers, boundary scan is something very, very unique to that particular thing. What that means to me is a continuity tester just means you built the board the way it was designed. Okay, functional test means it actually does what you intended it to do. There may be a different, or maybe built completely perfectly, but it may not function because you have tolerances and all the components and make sure everything balances out and such. So there's a little bit of audio on this one. I think you'll, as the EEs in the room, might find this to be interesting. Show us a little bit.
Historically, the most straightforward way to test electronic systems has been functional test. As the name implies, it means exercising a system as it is expected to be used in the target application. Though this approach continues to have merit, it has some significant drawbacks. First, it may be difficult to replicate a functional setup that sufficiently mimics the end application. Second, sufficiently testing the operational space of systems with even moderate complexity can be very difficult. An alternative to verifying functional operation is structural testing. This method tests individual partitions instead of looking at the system as a whole. It enables a more thorough testing that can verify corner cases, which are difficult to access using only functional test. Structural test also has problems to overcome. Gaining access to internal nodes is a challenge. One traditional method for accessing internal nodes is employing a fixture with multiple electrical contacts touching down on exposed metallic pads. This fixture is commonly called a bed of nails. Unfortunately, these fixtures are costly to fabricate and difficult to make a solid connection when there are many points to access simultaneously. This method becomes even more problematic as circuit technology shrinks with a higher reliance on multiple layered boards. It makes internal access almost impossible as nodes are buried under packages such as ball grid arrays. Boundary scan is an ingenious approach to structural testing that overcomes these challenges. Instead of relying on mechanical connections for access, it adds dedicated test circuitry to the system's ICs, using special registers inserted at the I/O pins. These registers can observe data on the I/O pins, and they can be used to override drive signals, providing test stimulus to the circuit. It's this combination of stimulating and observing internal nodes that provides a powerful mechanism for accurate structural testing. To gain test access to these registers, there's a separate serial data chain independent of the functional paths. Test setup information flows into the chain's input, propagating to the chain's output. If there are multiple ICs with boundary registers, they can be concatenated to make a longer chain. This same data chain is also used to offload measured data.
We could go on that, just it gets deeper and deeper as you go. But anyway, that kind of tells you a lot more functionally how you can exercise that circuit. The other thing is from an X-ray perspective. Used to be the parts were pretty simple, only on one side of the board. Now you got parts on both sides of the board. You got ball grid arrays, things like that. Now you have to be able to look underneath the part, inside the part, all around. So I'm going to show a quick example of an X-ray machine, and this is a three-dimensional X-ray machine. So you'll see it kind of moving around, and as it moves around, you'll actually, as it zooms in, you can see the solder balls like the ones I showed you. These little wires that are coming out here, those are the bond wires that are connecting the die onto the substrate. And these tunnels right in here, these are the vias that connect. You can kind of see them moving around in space as this moves in a three-dimensional way. But the vias connect it from one layer to the other layer going up and down in there. So you can see there's no shorts between any of these solder balls on here. So that's what the computer is looking for. If there wasn't solder on one of the balls, you would certainly be able to see it at this point also. Okay, conformal coating is basically on some downhole applications and other applications like might be susceptible to moisture coming in, and you want to be able to coat the board to make it a little bit less sensitive to other moisture. So think of this like spray painting. So you're basically spraying a material, and I think this is a good example of what that looks like. It actually covers the part. Obviously, you can't go underneath the parts, but it sprays everything. What you obviously don't want to do is conformally coat your connectors. So this is a three-dimensional machine. Actually, it's four-dimensional because it actually rotates, and it goes around and conformally coats the devices without doing any of the parts that you want not to be coated. And I'm not going to do this, but if you think of a ball grid array, you might have 1,000 interconnects on one device with solder balls on the bottom. So obviously there's no way to get a soldering iron in there. So what this does is this, for somebody that wants to remove a part off of a circuit board and put it back on again, it comes down, heats it up with hot nitrogen, gets the part good and hot without getting the other parts around it hot, and then it reaches down, grabs that part, pulls it up, and then you do it in reverse to put it back down. So you can unsolder and resolder components after assembly without bothering all the other parts in the area. And on the box build side, I'm not going to go into too much of that, but basically every circuit board's got to get placed into some kind of device, a cell phone, a car, something like that. And that term is called box builds. Okay, and there's some cool automation that's on the box builds here. See this, I think, in the Terminator movie for some reason. Yeah, I think that's the Mercedes-Benz plant, but it's pretty typical of what you would see at GM or anywhere else. A lot of the people are doing some of the inspecting and the lining, whereas the machine is doing the heavy stuff. You can see how it's just maneuvering a dashboard into there. I think that part was kind of interesting to see how those things are done. Automotive plants, we realize how much tooling they have to put in to get those factories running. Those are automatic screw machines, so you push the dashboard in and all the screws are all put in place on the robot over there. About 30 seconds. I thought it was kind of interesting to see the chassis moved in. It's basically got the transmission on it, and it just drops the top of the car on top of the bottom of the car, and then there's all the welding attaching the frame to the cover to the chassis. So if you think about it, think about how many engineers you need to design all of the machines that are involved here. What we're doing is we're taking the manual jobs that are very, very low skill, and we're giving a lot more jobs to all the people making all of the robots and machines and all that. It's a lot more satisfying to engineers to design things